Hi everyone, I'm going to discuss geometric sequence for today. And when we say geometric sequence, it's a sequence in which each term, except the first term, is obtained by multiplying a constant value to the previous term. And that constant value is we call as the common ratio. And in our discussion, we will denote the common ratio by small r. If we're going to compare this with arithmetic sequence, so in arithmetic sequence, to obtain the next term, we add a constant value. And we call that as the common difference. Here, we multiply a constant value to the previous term to obtain the next term. And we call that constant value again as common ratio in geometric sequence. So in working on the missing term of a geometric sequence, we consider this formula. Again, a sub 1 is the first term, while r is the common ratio, and n refers to the number of terms in a sequence. Now, the following terms or the following are examples of geometric sequences. Number 1 with common ratio equal to 2. So meaning we obtain the next term by multiplying the previous term by 2. For example, we multiply 10 by 2, we got 20. By 2, we got 40. And then by 2, we got 80. So this is also a geometric sequence with a common ratio equal to negative square root of 3. So we multiply the first term by negative square root of 3, we got negative square root of 3. We multiply negative square root of 3 by negative square root of 3, that's why we got 3. And then we multiply 3 by negative square root of 3. So we got negative square root of 3 until we got this negative 9 square root of 3. For number 3, just try to consider the two lowest values. So, and also consider the trend that the numbers are decreasing. So meaning the common ratio is less than 1. And then if we're going to consider this last two terms, consecutive last two terms, and we divide the last term by the second to the last term, we obtain 1/5, and that 1/5 will serve as the common ratio. So like if we multiply 15,625 by 1/5, or we simply divide 15,625 by 1/5, we got 3,125. 3,125 times 1/5 equals 625. 625 times 1/5 equals 125, and 125 times 1/5 equals 5. So this is also a geometric sequence. Now for number 4, the common ratio here is -1. We multiply the previous term by -1 to obtain the next term. For example, 1 times -1, we got -1, times -1, we got 1, times -1, we got -1, and so on. So this is a geometric sequence. For this, we can say that this is also a geometric sequence with common ratio equal to 3 halves, to 3 rather. So when we multiply 1/2 by 3, we got 3 halves. 3 halves times 3, we got 9 halves. And then 9 halves times 3, we got 27/2, or 27 halves. So these are all examples of geometric sequence. Now we're going to solve each problem here by considering or by working on some formula with geometric sequence. So here we're asked to find the 8th term in this geometric sequence. And solving for the nth term requires us to solve for this formula. And by substitution, we are actually asked to solve for a sub 8, and the first term here is 3. Now, by inspection, we select any two consecutive terms here, so we can solve for the common ratio. As we divide 12 by 3 here, we got 4, meaning the common ratio is 4. So as we multiply, for example, 4 to 3 here, we got 12. 12 times 4, we got 48. So really, the common ratio is 4. So we have 4 to the n minus 1. So since we are asked to solve for a sub 8, n is 8, and 8 minus 1 is 7. So this is to the 7th power. So evaluating this expression will come up with 49,152. Okay. So find the seventh term in the geometric sequence 2 over 9, 2/3, 2, 6, 18, and generate a pattern or formula. So this time we're asked to solve for a sub 7. And using again the formula a sub 7. So the first term here is 2 over 9. And the common ratio, of course, we're going to consider this one. If we divide 18 by 6, we got 3. So this is the common ratio. So as we multiply 3 from the previous term, we'll obtain the next term, like 2 over 9 times 3 is 2/3 times 3. We got 2 times 3, we have 6, and then times 3, we have 18. So this must be 3 to the n minus 1. So this is 3 to the 6. So evaluating this expression will come up with 162 as the seventh term. So write the first four terms of the geometric sequence. A sub n equals, by the way, for number 2, we are asked to generate a pattern or formula. So this is a sub n equals, so we will just have to follow the general pattern. No? A sub n quanta equals a sub 1 times r to the n minus 1. So since the first term is 2 over 9, we just have to multiply this by the common ratio, which is 3 to the n minus 1. So this is the pattern for number 2. So going back to number 3, so first four terms, we just have to solve for a sub 1 by substituting the given in this formula. So we have, so we know that the first term here is 2, and this is the common ratio. Okay, so a sub 1 is equal to 2 by inspection. And then a sub 2 is equal to 2 times the common ratio 1/2. Okay, so because this is n minus 1 and this is 2 minus 1, so the exponent will be to the first. And 2 times 1/2 equals 1. And then for a sub 3, actually no need for us to substitute the given in the formula. So from the definition of geometric sequence, the next term is obtained by multiplying the common ratio from the previous term. And we know that the previous term is 1. We'll just multiply this by 2. So we got 2 here. So the fourth term is multiplying 2 by 2. So we got 4. So we have, I'm sorry, it has to be 1/2. So wait. Okay. Let's go back with a sub 3. So the ratio is 1/2, not 2. So this is correct, a sub 2, but a sub 3 must be 1 times 1/2. So this is 1/2 for a sub 3. And then a sub 4 is 1/2 times 1/2. So it has to be 1/4. So the first four terms of this sequence is 2, 1, 1/2, 1/4. Okay. Find the sixth term of the geometric sequence whose first term is 1,000. So this is a sub 1. And whose fourth term is 64. So this is a sub 4. And we are asked to solve for a sub 6. Okay. So we can make use of this pattern again. A sub n equals a sub 1 times quantity times r to the n minus 1. So since we're asked to solve for a sub 6, again, the first term is 1,000. And then we do not know the value of r yet. But we know the fourth term. So instead, we substitute a sub n to a sub 4. So it must be 64. The first term is 1,000. We do not know r. Since we have substituted a sub 4 to a sub n here, our n is equal to 4. and then minus 1. So this is r cubed. So from here, simplifying the expression, so we have to divide both sides by 1,000 for us. So I isolate r cubed. So we have r cubed equals 64 over 1,000. Now we want to solve for r, so we have to extract the cube root of both sides. So this will be canceled. So we have r equals 60, cube root of 64 is 4, while cube root of 1,000 is 10. And this is equal to 2/5. So therefore, r is 2/5. So we can now solve for a sub 6. And a sub 6 equals, the first term is 1,000 times 2/5 is the ratio. And this has to be to the 5th power because we're asked to solve for a sub 6. Okay, so we now have, we have to evaluate the value here. So this is now equal to 125 over 4. So for this, we are asked to solve for the 10th term of the sequence. Okay, so we're asked to solve for the 10th term. By inspection, the first term is 2. And then by inspection again, the common ratio is, we select any 2 consecutive terms here. Like if we divide 2/3 by 2, so we'll come up with 1/3, and that's the common ratio. So when we multiply, for example, 2 by 1/3, it's the second term. Then 2/3 by 1/3, it's 2 over 9. So really the ratio is 1/3. So working on the 10th term, so this is a sub 10 equals the first term 2 times the common ratio 1/3, and this is to the 9th power. So evaluating this expression gives us 2 all over 19,683. There. Now, same with arithmetic series, we also have geometric series. This is the sum of the terms of a geometric sequence. So geometric series or not geometric series. Okay, so for number 1, are we gonna consider this as geometric series or not geometric series? Okay, so by inspection, we have 2, 3, 9/2, 27 over 4, 81 over 8. So we have here 2, and then we got 3. So meaning the ratio is 3/2. So we have to check whether 3, when multiplied by 3/2, will result to 9/2, which is correct. And then 9/2 times 3/2 is 27 over 4. And so with 27 over 4 times 3/2 equals 81 over 8. So this is a geometric series. For this, we have 1 minus 1/2. So this means 1 plus negative 1/2. And then plus 1/4. And then minus 1/8. So is this a geometric series? So we have to check if this belongs to geometric sequence. Now, if we consider r equals negative 1/2, and we multiply 1 by negative 1/2, we got negative 1/2. Negative 1/2 times negative 1/2, we got 1/4. 1/4 times negative 1/2, we got negative 1 over 8. So this is considered as geometric series. Okay, for 1 plus 4 plus 9 plus 16, all of these are perfect square expressions. And this is n squared. And the next term was not obtained by adding a constant value. So we do not consider this as a geometric series. This time, how do we evaluate a finite geometric series? Now, if you remember, we can evaluate the sum of finite arithmetic series. Same goes here with geometric series, finite geometric series. So if the sum represents, or if S sub n represents the sum of the n terms of a geometric series with first term a sub 1 and common ratio, take note, not equal to 1, then we have S sub n equals a sub 1 times quantity 1 minus r to the n all over 1 minus r. So that's the formula that we're going to use for finite geometric series. Okay, so we have S sub n equals a sub 1 quantity 1 minus r to the n all over 1 minus r. This is for r not equal to 1. Okay, so we're going to solve for the sum of integers from 100 to 999 that are powers of 3. So when we say power of 3, we consider that the ratio is 3. Okay? So from this interval, we have to look for a power of 3. So we have to identify a sub 1. Of course, we have to identify the last term, a sub n. Okay? So by inspection, so we have to consider power of 3 integers. Now, since 3 to the 4th equals 81, and 81 is not in the interval, so this is not a to the for a sub 1. So instead we move forward, like we evaluate 3 to the 5th, and we know that 3 to the 5th is 243. So we will consider this as our a sub 1. Now for a sub n, so by inspection, 3 to the 8 equals 6561, and 3 to the 9 equals, oh, wait. Let's, so we are not considering 3 to the 4th as our a sub 1. Instead, 3 to the 5th is considered as a sub 1. Okay, while 3 to the 8 is considered as our a sub 8. Okay, and this is our a sub n. Okay, so we have already a sub 1 and a sub n, which is a sub 8. So we can now solve for s sub n. In fact, n equals, so this is equal to, n is from this up to this. So the difference between this is 3 plus 1. So that's, we have 3 to the 5th, 3 to the 6th, 3 to the 7th, and 3 to the 8th. So we have 4. So we are solving for the sum of the 4 integers from 100 to 9,999, which are power of 3. So we have n equals 4 here. We are actually adding 3 sub 5, 3 to the 6, rather 3 to the 7, and 3 to the 8. Using this formula, we have S sub 4 equals 4 quantity. The first term is 243. And then the last term is 6,561. Oh, wait. This must be arithmetic series. Again. So we have a sub 1 here, which is 243. Quantity, so 1 minus 3 to the n, so n is 4, all over 1 minus 3. So evaluating the expression, we'll come up with 9,720. Okay. So this is equal to 9,720. So one day you saw an awesome video on YouTube at 1 p.m. You shared a video link to 5 unique people. Then 2 p.m. Then at 2 p.m. each of your friends share it to 5 unique people. If this pattern kept happening, then how many unique people received the link by 11 p.m.? So we have at 1 p.m. 5, and then 2 p.m. Each of these five person shares the link to 5 unique people. So that's, we have 25 at 2 p.m. And then until 11 p.m. Okay. Now we have to note that this problem is about geometric series, because for us, if this pattern kept happening, then how many unique people received the link by 11 p.m.? So we have to consider also those people who received the link prior to 11 p.m. Okay, so this is about working on the sum of all the people who received the link. Okay, so this is like identifying the value of n here. So we have 5 plus 25 plus, so if for example we proceed at 3 p.m., this would be 125 plus dot up to a sub n. Okay, so we know that a sub 1 here is a sub 1 is 5. Okay, and then r is 5 as well. So s sub n here is equal to, substituting the given in the formula here, we have a sub 1 equals 5, quantity 1 minus r to the 11. So how did we know that it's 11? Because this is from 1 p.m. until 11 p.m. So we have to 11, and then all over 1 minus 5. Okay, let me change r to the 11. So let me place the value of r to 5, replace. So evaluating the expression on the right side of the equation will come up with, imagine 61,035,155 unique people receiving the video link. Okay. So one summer vacation, you saw a plant on swimming pool. The following day, the plants were doubled on that same swimming pool. The pattern kept on repeating, and on the 10th day, the pool was full of plants. How many plants were there on the swimming pool? When was the pool was or half filled by the plants? Okay, so the first question is how many plants were there on the swimming pool? So it's on the 10th day that the plants were full of plants. No, I rather the pool was full of plants. Okay. So since the pattern, so since the plants are doubled every day, on each of the following day, it's doubled. So we consider that r equals 2, or the common ratio is 2. Now, since it started with one plant, so our a sub 1 is 1. So we assume that on the second day, this has 2 plants. Okay. So whereas on So on the 10th day, the pool was full of plants. So maybe we can solve for S sub 10 to calculate how many plants were there on the pool once it is uh, full with plants. No, so this is working on the formula S sub n equals a sub 1 times quantity 1 minus r to the n all over 1 minus r, and our a sub 1 is 1 times 1, and our r is 2. So this is from the first day to the 10th day. So this is to the 10th power all over 1 minus 2. And this gives us 1,023 plants. Now, the second question is, when was the full half filled by the plants? Since the common ratio is 2, the following day it's doubled, no? So every day that the plants are being doubled. So if on the 10th day, the plants, the pool was full, filled with plants. So a day before the 10th day, it will be half filled. Okay, so it has to be on the 9th day. So by inspection, when we solve for S sub 9, we have the first term a sub 1 equals 1, and then we have 1 minus, so this is 2 to the 9th all over 1 minus 2, and this gives us 511 plants. So it's correct, no? When you divide 1023 by 2, this is I guess 511.5. So this gives us 511 on the 9th day. So how do we evaluate infinite geometric series this time? So the sum of an infinite geometric series with first term a sub 1 and common ratio r is given by this formula. But there's a restriction that the absolute value of r is less than 1 only. Now, if the common ratio does not satisfy this required condition, then the series is divergent. So meaning we cannot evaluate the sum of this infinite geometric series. So we can solve for the sum of infinite geometric series if the common ratio is less than, or the absolute value of the common ratio is less than 1. And we can solve this by considering this formula. Okay, so we're going to evaluate if the geometric series is divergent or convergent. So if it's divergent, we write the infinity symbol. Okay, so for number 1, 16 plus 4 plus 1. So we have to check the two consecutive, the pattern is decreasing. So we can assume that the ratio is less than 1. And then by inspection, checking on consecutive terms, we have, or dividing any among consecutive terms, or if we're going to consider 4 and 1 here. So we divide 1 by 4, it's 1/4. So meaning the ratio is 1/4. So to obtain the next term, we multiply the previous term by 1/4. So with this, r equals 1/4. And we consider that, so we can solve for this geometric series. And how do we solve for this? This is S sub n. So the first term is 16 all over 1 minus the common ratio 1/4. So evaluating this expression will get 64 over 3. Okay, for number 2, so the pattern is decreasing, the terms are decreasing, and looks like each term is obtained by dividing the previous term by 2, or simply multiplying the previous term by 1/2. So with that, absolute value of r is less than 1. In fact, r equals 1/2. So we can solve for S sub n here. So we know that the first term is 600 all over 1 minus the common ratio 1/2. So we have 1,200 as the sum of this infinite geometric series for number 2. And then for number 3, we know that it's an infinite geometric series with common ratio equal to 1/2. So we can solve for the sum. And S of n equals, the first term here is 1, and then all over 1 minus 1/2. So we got 2 as the sum of this infinite geometric series. For number 4, the common ratio is 3/2. Therefore, we cannot evaluate the sum. So we just represent this by the infinity symbol. So this time we go with geometric means. So when we say geometric means between two numbers, we can find any geometric means between two numbers or geometric sequences. So it follows that geometric means of two numbers form a geometric sequence with that given numbers. So for example, we're asked to find the geometric mean of 8 and 18. So what we're going to do is to consider, or we are actually going to solve for a sub 2. Since the first term is a sub 1 and the last term is a sub 3. And we have to substitute the given. So we have 18 equals a sub 3. So the first term is 8. And then we do not know the ratio. But this is r to the n minus 1. So this is the general pattern. Remember, we have a sub n equals a sub 1 times quantity r to the n minus 1. And substituting the given here, substituting the given to the formula, we have a sub n equals 18. So this is a sub 3. And then 8 is the first term. So this has to be r to the n minus 1. Since we have medius of 18 as a sub n, then our n is 3. So 3 minus 1 is 2. So this is 18 equals 8r squared. We want to solve for r, so we have to isolate r squared. So we have to divide both sides by 8. So we got r squared equals 18 over 8. 18 over 8 is the same with 9 over 4. And then we extract the square root of both sides. So we got r equals 3/2. So since r equals 3/2 and we know that a sub 1 is equal to 8, working on the geometric mean is obtained by just multiplying the previous term 8 by its common ratio 3/2. So we have 12. So the geometric mean for the geometric mean of 8 and 18 is 12. Now here we're going to insert 3 geometric means between 81 and 8561. Take note that this is a sub 1 and this is a sub 5. So substituting the given in the formula, we have 6561 for the fifth term equals the first term a sub 1, 81, and then this is r to the fourth. So we divide both sides by 81. So we have r to the fourth equals, so 6561 when divided by 81 equals 81. So r to the fourth equals 81. Extracting the fourth root of both sides will obtain r equals 3. So we can work on the 3 geometric means by solving for the first geometric mean a sub 2. So we multiply this by the first term 81 by 3. So 81 times 3 is 243, while a sub 3 is 243 times 3. So we have 729. And then a sub 4 equals 729 times 3, 2187. So these are the 3 geometric means. Okay. Now, I want you to solve for this problem involving geometric series and geometric sequence. A small school has started in 2015 with 120 students. It is estimated that the student population will increase by 3% each year. Write a formula for the student population. So that's the first thing that we're going to do. And then the second one is you're going to estimate the student population in 2021. I want you to write your answer in the comment box section of this video. So with the discussion that I have made about geometric sequence and geometric series, you will be able to solve for this problem. So I'm looking forward to your answer on the comment section of this video. So bye for now.